Hi everyone. In this mini lecture, we're going to talk about the classification of lattices. So in the last mini lecture, we talked about Bouvet lattices and some different items of terminology associated with them. At the end of that mini lecture, we started talking about the Wigner-Seitz primitive cell, which is an object that in some sense captures the symmetry properties of the underlying lattice. So symmetry is a very important concept in all of physics. It has to do with things like ferromagnetism and superconductivity. It's also obviously important for the study of crystals. And it turns out that symmetry is one of the underlying considerations when we talk about classification of different kinds of lattices. So in this mini lecture, we'll talk about the different kinds of 2- and 3-dimensional lattices. And again, we classify them via their type of symmetry. So there are 5 different Bouvet lattices in 2 dimensions. So we'll talk about these different kinds of lattices. The first is the square lattice. This looks, not surprisingly, like a square array of points. We might choose primitive lattice vectors A1 and A2 that look like this. And the Wigner-Seitz primitive cell looks also like a square. This kind of lattice is symmetric under reflection about the X and Y axes and 90-degree rotations. By the way, we're talking about 2-dimensional lattices because it's a little bit easier to understand and visualize than 3-dimensional lattices. After we finish with these 2D lattices, we will indeed talk about some of the common 3D lattices. The next type is called the rectangular lattice. This looks, not surprisingly, like a rectangular array of points. We might define lattice vectors A1 and A2 like this. The Wigner-Seitz primitive cell also looks like a rectangle. You can see that this is a less symmetric lattice than the square lattice. So it loses the symmetry under 90-degree rotations, but it is still symmetric under X and Y reflections. The next type of 2D Bouvet lattice is the hexagonal lattice. So it looks like this. We might define primitive vectors A1 and A2 like this. Notice this is not the same as the honeycomb lattice. If you like, there is a point in the middle of each hexagon. The Wigner-Seitz primitive cell for this hexagonal lattice might look something like this. It is still a hexagon. This is symmetric under reflections about the X and Y axes. And 60-degree rotations. We can think about graphene, which you recall is a honeycomb lattice. As a hexagonal lattice with a 2-point basis. So every point that I circle here would be part of the underlying lattice, and each lattice point, if you like, has a 2-point basis. All right. The next type of 2D Bouvet lattice we can think about is called the centered rectangular. Lattice. This is like a rectangular lattice with points in the middle. And the Wigner-Seitz primitive cell looks like kind of a squished hexagon. This you can arrive at by compressing the hexagonal lattice. The symmetry properties are the same as hexagonal, but without 60-degree reflection symmetry, or rather 60-degree rotations. The last type of two-dimensional lattice is the oblique lattice. We have seen this before. The Wigner-Seitz primitive cell looks like this kind of an object. And this one is the least symmetric of the 2D lattices because it has arbitrary A1 and A2. It has only inversion symmetry. Okay, let's just talk about a few more items of terminology having to do with symmetry. When we think about rigid motions, mathematically we can describe any rigid motion as the sum of a displacement and a rotation by some angle theta around some direction n with center r. So this is kind of unusual notation, but it's again supposed to mean that any rigid motion of an object can be decomposed into displacement by a vector and some arbitrary rotation. So the set of all rigid motions is a group. In the mathematical sense, because it's closed, it has a natural product and an identity operation. So we'll say the space group again, group in mathematical sense, is the group of all rigid motions that leave a lattice unchanged. And now we come to classification of lattices. This is done according to the different symmetry groups of this is done according to different symmetry groups that are respected by the different types of lattices. All right, so just as we said before that any rigid motion can be decomposed into the sum of displacement and rotation, we can compound any symmetry operation of a Bouvet lattice out of translation through a lattice vector and a rigid operation, leaving a lattice point fixed. So A good example of this is if I take 4 lattice points, 1, 2, 3, 4, and if I rotate them about the center by 90 degrees, 1, 2, 3, 4 go to 2, 3, 4, 1. So that is a symmetry operation, but it didn't leave any particular lattice point fixed. I can decompose this symmetry operation into the following sequence. Here's the original set of lattice points. Let me translate them down by one lattice vector. So 1, 2, 3, 4 go to 1, 2, 3, 4. Now let me rotate by 90 degrees about 0.1. So then I have 1, 2, 3, 4. So you see this arrangement of points over here is the same as this arrangement, but in the latter case, I got from the initial arrangement to the final arrangement by translating through a lattice vector and performing a rigid operation that leaves one lattice point fixed. So the we'll introduce one more piece of terminology here, which is the point group. And that is the group of operations that leave a lattice unchanged It's the group of operations that leave a lattice unchanged and map a point in the lattice back to itself. So we'll say that two different lattices belong to the same crystal system. If they have the same point group. Okay, so they don't need to be the same lattice, but if they share the same point group, they belong to the same crystal system. So again, they don't need to have the same space group, which is the total group of symmetry operations, but they need to have the same point group. And these are how the crystal systems are determined. So in just a little bit, I'll show you the different crystal systems in 3 dimensions. You should know there's a rather significant and involved terminology for classifying different lattices. I encourage you to read about it in Ashcroft and Mermin. I'm not a crystallographer, so I won't go into too much detail about this in this course, but if it's something you're interested in, please have a look in Ashcroft and Mermin. All right, so let's talk about some common 3-dimensional lattices. So the first 3-dimensional Bravais lattice that we should talk about is simple cubic. Not surprisingly, it looks like a cube. And a common choice of lattice vectors are these, A1, A2, and A3. It is very uncommon for elements to occur in the simple cubic form. In fact, only polonium, poisonous radioactive element, occurs in simple cubic form. Another 3-dimensional Bravais lattice that's worth remembering is body-centered cubic. So this looks like a cube with an additional point right in the middle of the cube. It's in the center of the body of the cube. And so a common choice of lattice vectors might be A1 here, A2 here, and then A3 will go from this point of the cube to the center of the body. And here my axes look like this. So one choice of the primitive lattice vectors for the body-centered cubic, sometimes this is called the BCC lattice, are A1 is equal to AX hat. So A will be the length of the side. A2 is a Y hat, and A3 is A over 2 X hat plus Y hat plus Z hat. We can, as we've said before, choose any other set of primitive lattice vectors we wish. Another set that's perhaps more symmetric is the following. Okay, BCC is a common lattice for different kinds of elements. Things like argon, silver, aluminum, gold, copper, nickel, and lead occur in the BCC structure. We also have face-centered cubic. This looks like a cube. But now we put an additional lattice point on the faces of the cubes. And we can define a set of primitive lattice vectors, for example, to go from the corner of the cube to the nearest points on the centers of the faces. So we might define, for example, A1 is equal to A over 2 Y hat plus Z hat. A2 is A over 2 Z hat plus X hat. And A3 is A over 2 X hat plus Y hat. And again, A is the length of the side of the cube. Now, elements that occur in the FCC structure include barium, chrome, iron, potassium, lithium, molybdenum, sodium, and tungsten. So these two, BCC and FCC, are rather common. We can also construct a hexagonal three-dimensional Brevet lattice. It looks like triangular nets that are stacked on top of each other. So on and so forth. And if A is the distance from here to here, and if C is the distance from here to here, we might define primitive vectors in the following way. A1 is AX hat, A2 is A over 2 X hat plus root 3 over 2 AY hat, and A3 is C Z hat. The diamond lattice is two interpenetrating FCC lattices. if you like, it's an FCC lattice with a basis. This is also common. It's not surprising that carbon occurs in the diamond structure, also silicon, germanium, and tin. Zinc blende is similar to diamond, except that the 2 points have different atoms on them. So compounds with the zinc blende structure include zinc selenide, cadmium telluride, mercury telluride, aluminum arsenide, and gallium arsenide. These are all extremely useful and common semiconductor compounds. The sodium chloride structure is also an FCC lattice with a 2-point basis. It's slightly different than the zinc blende structure. Obviously, sodium chloride occurs in this structure. One can also have simple cubic with a basis. This is the cesium chloride structure. So in case I wowed you too much with my drawings of the lattices and you were just overcome with their beauty to fully appreciate them, let me show you a PowerPoint slide of some of these lattices. Then we'll talk about the different crystal systems in 3 dimensions. So we're going to go over to the PowerPoint slide here. So here are some common lattices in 3 dimensions. Here is the BCC lattice. Again, you see it's a simple cubic lattice with a single point in the middle. Here's the lattice itself with the Wigner-Seitz primitive cell. Here's the FCC lattice. You see that it's a simple cubic structure, but with 1 extra lattice point on the faces of the cube. Here is the FCC lattice, the unit cell with the Wigner-Seitz primitive cell in it. Here's the diamond structure. This is 2 interpenetrating FCC lattices. If you like an FCC lattice with a basis. Here's the sodium chloride structure, also an FCC lattice with a basis, and the cesium chloride structure, which is just simple cubic with a basis. So these pictures are all from Ashcroft and Mermin. There are a number of other good pictures of crystal lattices in this book. Now let's talk about the different crystal systems in 3 dimensions. Remember, these are the systems in which the different lattices have the same point group. So the first crystal system to think about is the cubic crystal system. This includes things like simple cubic, BCC, and FCC. The point group of the cubic crystal system is the symmetry group of a cube. One can reduce the symmetry of this group by elongating one of the sides of the cube. So if you like, we pull it up a little bit, we go from cubic to tetragonal. So this is a lower symmetry group than the cubic group. This includes things like simple tetragonal, centered tetragonal. We can further reduce the symmetry of the tetragonal group by elongating, again, another one of elongating along another direction of this cube. We end up with orthorhombic. There are lattices like simple orthorhombic, base-centered, body-centered, and face-centered orthorhombic. We can go from orthorhombic now to monoclinic. This is obtained by distorting the rectangular faces perpendicular to the c-axis into parallelograms. So if you like, all of the faces of the orthorhombic structure are rectangles. Now we make some of those rectangles into parallelograms, and we can reduce the symmetry even further by going to the triclinic group, where we tilt the c-axis. We have in monoclinic group the c-axis making a right angle with A or B here. Now we relax that restriction here. So the triclinic is the least symmetric of the 7 crystal systems. Going up to trigonal, we can arrive at a trigonal lattice by pulling along the body diagonal of a cube. And finally, we have the hexagonal crystal system, which is like a hexagonal prism with a hexagonal base. So if we include lattices with bases, there are 32 possible point groups and 230 possible space groups in 3 dimensions. So as I said, there's a detailed and somewhat complicated nomenclature for these different symmetry groups. I encourage you to read about it in Ashcroft and Mermin. Knowing and being comfortable with crystal systems will pay dividends later on in this course as we talked about the effect of periodic potentials on electrons.